Hello students, welcome to Narayan PU College online classes. So in the last video we have discussed about the chemical properties of HNO3. Still we have not completed. So we are discussing about reaction of metals with the HNO3, right? So in that one we have discussed first category, that reaction of the metals which are less electropositive than the hydrogens. Means less means you already know that more electropositive than the hydrogen, that we have discussed. Means metals are which are more reactive, and those metals how they react with the HNO3, that we have discussed. Clear? And mainly you know that when concentrated HNO3 is act as oxidizing agent, one of the products should be NO2. When dilute HNO3 is act as a oxidizing agent and it reduced it to NO. Clear? So only magnesium and manganese when reacted with dilute or very dilute HNO3 and produces metal nitrates plus hydrogen. Remaining metals will not produce any hydrogen here. Clear? Ma? So in that one hydrogen produced, but what happened, that hydrogen will be utilized to reduce the HNO3 to give the different products. Clear? So in that one very important reaction with the zinc. When zinc reacted with the concentrated HNO3, as usual reaction, zinc is converting to zinc nitrate and HNO3 is reduced to NO2. Clear? But the thing is here, when it is reacted with the dilute HNO3. Usually dilute HNO3 means we should get the NO, it should reduce it to NO, but here the HNO3 is reduced to N2O, that you have to remember. Clear? No? And also how tin reacted with the lead tin, how they reacted with the concentrated HNO3 and dilute HNO3, that we have already discussed. Clear? No? So next concept here is passivity. Put the heading passivity, important for competitive examination. Clear? Ma? So what passivity means? Some metals like iron, chromium, nickel and aluminum, when dipped into the concentrate HNO3 and they lose their normal reactivity, or you can say normal activity, and become passive. Clear? Ma? So if you take the metals like what it is, ma? Metals like what it is, ma? Here mainly iron, metals like iron, chromium, nickel and what it is, ma? Here aluminum. Mainly these metals will show the passivity. Passivity means what? They losing their reactivity. When you dip those metals into the HNO3, concentrated HNO3 is called as a what it is, ma? Here, and they become a passive. Passive means what? Losing of their normal activity. Clear? So what is that reason for this? Clear? The passivity is due to formation of protective layer of the metal oxide over the surface of these metals, and which prevents the further action. Clear? So that we will call as a passivity. Metals like iron, chromium, nickel and aluminum when dipped into concentrate HNO3 lose their normal activity and become passive, and become what it is, ma? Here passive. Clear? So in the competitive examination directly they will ask which of the following metals and show the passivity with the concentrated HNO3. Mainly what it is here, ma? Iron, chromium, nickel and aluminum. So what is the reason for this? What is the reason? Why? Because means the passivity is due to what it is, ma? The passivity is due to formation of protective layer of which one, ma? Protective layer of metal oxide on the surface of metal, on the which one here? Surface of metals, on the surface of metals. Clear, no? So this is the what it is here, passivity. Clear? So metals like iron, chromium, nickel and aluminum dipped in the concentrate HNO3, they lose their activity and become a passive. And why they become a passive means, because the passivity of these metals are due to formation of protective layer of metal oxide on the surface of the metal. Simple. Suppose if I take here iron, I will write the reaction also. Take the iron here, clear? So when this iron is dipped into the concentrate HNO3, there will be a formation of iron oxide layer around the surface of this iron. This is what it is, iron, and this is what it is, iron oxide layer. Iron, simply we can write here, iron oxide layer. Clear? So that's why, and this is a one protective layer. So that's why iron will not show their reactivity with the other compounds, because there will be a layer around the what it is, iron oxide layer, metal oxide layer around the metal. So this iron oxide layer prevents the metals to react with the other compound. That we will call as a passivity. Clear? Simple. If I write here simple example and take the here equation, iron plus, I will write there, that side I will write. Clear? Take here iron. Clear? Iron and plus concentrate HNO3. Concentrate HNO3. What you will get here is iron oxide, Fe3O4. It is a mixed oxide like FeO and Fe2O3. Mixed oxide we will call. And plus what you will get here? NO2 plus you will get the H2. NO2 plus what it is? H2. Clear? So you know that actually iron should convert it into, according to our reactions, you know, metals should convert into metal nitrates. Clear? But you see here, is there any metal nitrate formation takes place here? No. That is what it is here, metal oxide takes place. That we will call as a passivity. Clear? Balance here, if you take this is 8/3. Clear? And 0 to 8/3 this is, and here plus 5 to, you know, this is a plus 4. This is plus 5 and plus 4. Here it change decrease oxidation state 1, but here increased oxidation state is 8/3. 8/3 means I have to multiply this one with the 8/3, and I have to multiply this one with the 8/3, and this also I have to multiply this one with the 8/3. Clear? But you know 8/3 means a fraction, so multiply total reaction with the 3. Clear? Then what I will get here? 3 moles here. Into 3 means you will get 8, and then already 3 irons are there, and 8 NO2. Hydrogens are how many? 8. So that's why I have to take this is 4. Clear? So this is what it is, my balanced reaction. Instead of getting iron nitrites, what you are getting here? Iron oxides. Clear? So this is about the passivity of what it is, here metals which are more reactive, are more electropositive than the which one here, hydrogen. So now that concentrate HNO3, how it reacts with the highly reactive metals, that we have completed. Now a reaction with metals which are less electropositive than hydrogen means, you know, I already mentioned, if you have studied in the means redox reaction, you might have studied in the redox reaction, you know, electrochemical series we have given, and it will also come in the electrochemistry chapter, that also we will discuss this concept. So hydrogen will be in the middle, above the hydrogen metals will be there, and below the hydrogens metals and also non-metals will be present. And metals which are present above the hydrogens are very, very reactive, that we have already discussed, like sodium, potassium, magnesium, zinc, all these are. And metals which are placed below the hydrogen are less reactive. Clear? Like copper, you know, copper is there, silver and gold. Clear? So all these compounds are, means metals are there. How these metals, less reactive metals we will call copper, silver, gold, platinum, mercury, all these are placed below the hydrogens, and those are less reactive compared to the and previous what we have discussed metals. Clear? So how it will react with the copper? You know, copper is a less electropositive, and how it will react with HNO3. Clear? So as I already mentioned, one is concentrate HNO3 and another one is dilute HNO3, and you know how to balance the equations. Again I will not balance here. Clear? So when I take here concentrate HNO3, you already know what are the products. Metal will be converted into metal nitrite, and metal nitrate, and HNO3 concentrate HNO3 is converted into NO2. Clear ma? So that is what the compound you will get, copper nitrate NO3 twice plus what you will get ma, NO2 plus what you will get ma here, H2O. And if you balance, you will get here 4 moles of HNO3, 4 nitrogens are there here, you have to take here 4, and here hydrogens 2 or 4 are there, and multiply this one with the 2. You know how to balance this, use the same ion electron method you will get. Clear ma? So in the same way, copper react with dilute HNO3. Clear ma? Dilute HNO3. What is the product? Clear? So when it is dilute HNO3, same, and you have to take here 3 moles and here 8 moles, balance, you will get it CuNO3 twice. Clear ma? Same compound, and instead of NO2 what you have to get, dilute means NO plus what it is ma, and H2O. Where the difference you will get with the zinc what you will get, if you take zinc you will, with dilute HNO3 N2O you will get, not NO. Clear? So now balance, here 3 coppers are there, and here 3 coppers, 8 nitrogens are there, here already 6 are there, and here I have to take the 2 moles, and hydrogens 8 are there, 8 means I have to take here 4. Clear no? So how these are? So this is about with the copper. This is what it is ma here, with the copper. And second one is with silver. With silver, same Ag plus HNO3 is giving rise to same compound you will get, AgNO3 twice plus NO2 plus what you will get ma here, H2O. So if you balance here, what you will get is, and here plus 1, so you will take here 2 moles, and if you take 2 moles here, then I have to take 2 moles, and here H2O. It is a balanced, because NO3 are 2 here and NO3 are 1 here, so I have to multiply this one with this. And second one, this is which one here? Concentrate. I have written here NO2 means it is a which one? Concentrate. In the same way, Ag reaction with dilute HNO3. Clear ma? Which one here? Dilute HNO3. And same balance, you will get the same reaction here, AgNO3 twice plus what you will get ma? NO plus what you will get here, H2. Clear ma? Same balance here, 3 moles and 4 moles. And I am not saying here again and again balancing, I have already done how to do this. Clear ma? And for here, if you balance the compound, 3Ag plus 4HNO3 means 4 means, or here not 4, actually we have to take. So here you should not get AgNO3 twice. Clear? It is a mistake, because Ag having the valence is 1, NO3 also having the valence is 1, so that's why don't write, sorry, this is AgNO3. By mistake I have written AgNO3, and here also what you will get ma? AgNO3. So here 3Ag and 3Ag, so here 4 NH3s are there, and 3 here and 1 here. It is already balanced. 4 nitrogens are here 3 nitrogens, and here 1 nitrogen. Hydrogens are 4, and so that's why 2. This is about the what it is ma here, reaction of HNO3 with the less electropositive metals. So this is about the what it is ma, chemical properties of metals. Clear? And the next one, as I already mentioned, and here gold concentrate HNO3, it can attack all the metals except the which one ma? Except the noble metals. What are the noble metals? One is the gold and another one is the platinum. Clear? So but if you take mixture with the HNO3, if you add some HCl, mixture of HNO3 and HCl can react with the noble metals. Clear? So that we will discuss here. Next one is, put the heading, reaction with what it is ma here, noble metals. Reaction with noble metals. Clear ma? So what are the noble metals here? Silver and not silver, mainly gold and platinum. Clear? And you know that concentrate HNO3 alone cannot react with the noble metals. So but you take here mixture of concentrate HNO3 and HCl. If you take that mixture and these noble metals will react, you can say will dissolve. Clear ma? So what is that one here is noble metals dissolves in aquaresia. Very important, this is aquaresia. Clear ma? So dissolves in aquaresia and give their respective and forming their respective chloride and forming their respective chlorides, what it is ma here, chlorides. Okay, and very important here, aquaresia. What is the aquaresia? Clear ma? So this is aquaresia. Aquaresia is a three parts of HCl plus one part of concentrate HNO3. One part of what it is ma, concentrate HNO3, and that mixture we will called as a aquaresia. Very important in the competitive examination. Means if you take 3 moles of HCl, you have to take 1 mole of HNO3, like that it is. Clear ma? So very important for the competitive examination also. They will ask what is the aquaresia. So 3:1 ratio of HCl and what it is ma here, HNO3, or simply you can write here concentrate HCl plus concentrate HNO3. In which ratio ma? 3:1 ratio. Clear ma? So why these metals will react or will dissolve in the aquaresia but not in concentrate HNO3? That is means, you see, if it is Y means 3 moles of HCl first reacted with the concentrate HNO3 and it gives nitrosyl chloride. One NO and Cl will be removed as a NOCl plus H2O. Plus what it is ma here, H2O. And if you take here, how many hydrogens are there? 3 and here 1, 4. So that's why I have to multiply this one with the 2. Clear ma? 1 here NO and Cl. Total how many oxygens are there? 3, and here 2 and here 1. But chlorines are not balanced, you see. Here 3 chlorines are there and here 1 chlorine. So that's why it gives 2 nascent chlorines. And this we will called as a nascent chlorine. You know that nascent chlorine or nascent hydrogens or oxygens are very reactive. So that's why, and if you take the concentrate HNO3 and concentrate HCl mixture, if you take, and they produces the nascent chlorides. Clear ma? Nascent chlorine here. This chlorine being a more reactive will react with the what it is ma here, metals. Will react with the what it is here, will react with metals, noble metals. You know, first one, if I take here Au, clear, it will react with highly reactive nascent chlorine and it gives here AuCl3. Clear? Auric chloride. What we will call this is auric chloride. Rm we will call gold. Clear ma? Auric chloride. Clear? And now, and this AuCl3 and react with, we have taken here excess amount of HCl, and this AlCl3 will dissolve and gives the compound is here AuCl4 complex. Clear ma? So this is for which one here, gold. In the same way, platinum also will react with the nascent chlorine which is produced by the aquaresia and converted into platinum tetrachloride. What it is ma here? Platinum tetrachloride. And this platinum tetrachloride again will react with the dissolves in the excess amount of the HCl. You will get the compound is H2CP2Cl4. This is chloroplatinic acid. What it is ma here? Chloroplatinic acid. Platinic acid. chloroplatinic acid. See, so that's why here, noble metals will easily dissolve or easily react with the aqua regia, but not alone with HNO3. Clear ma? So this is about the what it is ma here compound platinic chloride, and this is arochloric acid. This is chloroplatinic acid, and this is arochloric acid. Clear? So this is about the reaction with noble metals. Clear ma? So next concept is here a reaction with organic compounds. Clear ma? So you know that, and concentrate HNO3 and nitrating mixture we have studied in the organic chemistry. Clear ma? So, and those reactions we will discuss here. And if I take here, suppose first one, benzene. You studied this one in the first year. Benzene and reacted with the concentrate HNO3 and concentrate H2SO4. What we will call this is nitrating mixture. You will get the compound is nitrobenzene. What you will get my compound here? Nitrobenzene. This we will called as a nitrobenzene. Clear? And in the same way, if I take here toluene, what is the toluene formula here? So this is CH3. This is the toluene. Clear ma? So this is reacted with concentrate HNO3. Take the 3 moles of concentrate HNO3. Then you will get the compound here is, as you know, and CH3 is a electron donating group and it activates the ortho and para positions, NO2, and here what it is ma here NO2. What we will call here 2, 4, 6 trinitro trinitro what it is ma here toluene. Clear ma? So this can also be called as simply TNT, trinitrotoluene. Clear? So next one, in the same way, if I take here phenol is treated with 3 moles of concentrate HNO3. This is also we have discussed in the alcohol, phenols and ethers. You will get the compound here is what you will get ma picric acid 2, 4, 6 trinitrophenol. What we will call ma this is simply picric acid. You see, so in all these compounds, organic compounds reacting with which one ma HNO3 only. In the same way, glycerol. Clear ma? So glycerol means what is the formula here? CH2 CHOH and here OH and CH2OH. When it is reacted with 3 moles of concentrate HNO3, 3 moles of what it is ma here concentrate HNO3. Concentrate HNO3 means what I can write ma here OH and NO2. Clear? 1 H and 1 OH will be removed. Clear? This is like H and OH will be removed and NO2 will be added. CH2O NO2. Like that product you will get. Clear ma? So what the product you will get here is trinitroglycerol. What you will get the product ma here? Trinitroglycerol. Clear? And H and plus. So what you will get here? You will get the compound is CH2ONO2. Clear ma? And here CHONO2. In the same way CH2ONO2. What we will call this compound, and 3 moles of what we will get ma 3 moles of water will be released, and here OH is there and H, remove water. Here also OH and H, remove water. So this we will called as a trinitroglycerol. This is glycerol. Okay? So this TNT and this trinitroglycerol are used in the explosives. Clear? So this is about the chemical properties of what it is ma here HNO3. And the next concept it is there here, brown ring test. So next one is here brown ring test. Clear ma? And this test is used to identify the nitrate ions. Very, very important. Brown ring test is for which one, here? This brown ring test is for nitrate ions. Nitrate ions. What are the nitrate ions? NO3 minus. Clear, ma? So what we will do actually in this? Clear? So what we will do, first of all, we will take the one test tube. Clear, ma? Take the test tube here and add solution of nitrate. Add the which one, ma, here? Nitrate solution. Take any potassium nitrate you take, or sodium nitrate, NaNO3, KNO3, that solution you take. This is the first one. You have to take the nitrate solution. You have to take the first, what it is, here? Nitrate solution. This is the first step you have to do. Clear? And second one. Second step, what you have to do is add here, this is the second step. Add freshly prepared FeSO4, ferrous sulfate. Clear, ma? Freshly prepared FeSO4. Clear? That is the second step you have to add. And third, after adding that, you have to add the concentrate HNO3. What you have to add, ma, here? Concentrate, sorry, H2SO4, not HNO3. So you have to add here concentrate H2SO4 drop wise along the walls of the test tube. You should not add at a time. You have to add take the dropper and take the concentrate HNO3 and slowly take the test tube here, slowly add drop wise into the along the walls of test tube to the solution. Clear, ma? And then you will get the the appearance, you will get the one brown colored ring will be appeared here. What it is, ma? Brown colored ring like appeared at the junction of two layers. Means when it touches this concentrate H2SO4 to this layer, then automatically that at the junction and formation of brown colored ring appeared. So that's why we will call it is a brown ring test. Clear, ma? So this indicates brown ring indicates the presence of nitrate ions in the solution. Presence of nitrate ions in the solution, and this is we will call it as a what it is, ma, here? Brown ring test. Clear? So why this color appears and what is the what is the for which compound is formed when we add the FeSO4 and H2SO4 this nitrate solution? What is the reason for, what is the compound responsible for that brown colored precipitate? Clear, ma? That we will discuss. And first of all, we have taken which one, ma, here? Nitrate ion. What is the nitrate ion formula? NO3 minus plus. Clear? What we added here? Freshly prepared FeSO4. FeSO4 means what it is, ma? Fe plus 2 ions. I am writing in the form of ionic equation. Clear, ma? Fe plus 2, because Fe plus 2 and SO4 2 minus. So that's why Fe plus 2. Then what I added, ma, here? Acid. Acid means what it is, ma? H plus ions. Clear, ma? Then what you will get? So you will get the compound here is Fe is converted into Fe plus 3 and NO3 minus is converted into NO and hydrogens will be converted into H2. Clear, my dears? This is the reaction. You observe clearly here. Fe plus 2, it is in the form of plus 2 and here in the form of plus 3. Plus 3 means what it is, ma? It is oxidized. It is oxidized means it acts as a which one? Reducing agent. It reduces the HNO3 into NO. Clear, ma, here? So the reaction, the formation of reaction, it depends upon the reducing capacity of the Fe plus 2 ions. Clear, ma? And these Fe plus 2 ions and remaining Fe plus 2 ions, we will take the FeSO4 excess amount, will react with the nitric oxide which is formed in this reaction. So Fe plus 2 in the solution, we added here FeSO4 into the solution. It is in the form of now Fe H2O 6 times plus 2. This is. In the water, iron will form here coordination complex that I have written here. But it is in which form? Plus 2 form only. Will react with NO which is formed here. NO which is formed. Then you will get the compound is Fe H2O, one water molecule will be removed. Instead of that, you will get the NO. This is plus 2. Clear? And this is the compound responsible for the brown colored, brown precipitate. Clear? So very important here. And sometimes what they will ask, and balance here, if you balance, take here, means the same oxidation number method you do, and you have to multiply here plus 5 and here plus 2. Difference how much? 3. So that's why I have to multiply with the 3, and this I have to multiply with the 3. Then automatically will you balance here. And NO3 is there, and here there will be a NO and H2O. So hydrogens you have to balance it here. Hydrogens, if I take here 4, then I have to multiply this one with the 2. Why? Because here 3 nitrogens oxygens are there, but here 1 oxygen and here 1 oxygen. So that's why I will multiply this one with the 2, then 3 oxygens will be there, and 4 hydrogens are there, multiply this one with the 4. That is the balancing equation. And very important here, why this brown precipitate comes means because of charge transfer. Because of which one here? Very important. Because of charge transfer. Charge transfer from where to where? From the ligand to metal. So it is because of charge transfer from ligand to metal. Ligand to what it is here? Metal. Very, very important question for the competitive. Because charge transfer 4 are there actually. Ligand to metal charge transfer, metal to ligand charge transfer, metal charge transfer, ligand charge transfer. They may ask. And here in the brown ring test, the brown colored precipitate is formed here responsible. The brown color is responsible for which type of charge transfer? They will ask ligand to metal, or metal to ligand, or metal or ligand. What you have to choose here? Ligand to metal. How it will be? You take this compound here. You know actually the plus 2 charge is there. What is the oxidation state of the iron here in this complex? Also sometimes they ask question. It seems like it is a plus 2, but it is not a plus 2, it is a plus 1. How means if you take this compound FeH2O and 6 times and NO. Clear ma here? So actually the plus 2 is belongs to iron, because you see here oxygen, you know, H2O neutral molecule, plus 2 is belongs to which one? Iron. But here later what it is entered? NO. You know that previous I already mentioned, NO is a it is a odd electron molecule. It is a which molecule? Odd electron molecule. Means it is having 1 electron here. Means here lone pair of electron is there, along with that 1 electron is there here. Clear? So what it will do? It donates this electron, it gives these electrons to metal. These we will call as a ligands. H2, sorry, it is here 5 times, and here 5 times. H2O and NO, these we will call as a ligands. Clear? This is a central metal atom. So that's why the electron is transferred from the ligand to which one? Metal. Means what happened here? Ligand is losing electron, metal is gaining electron. When it is metal gaining electron, should get the negative charge. 1 negative charge. Already plus 2 is there, minus 1. You will get what it is? Fe plus 1 and H2O 5 times. And here NO is losing 1 electron, so it plus. Clear? So here 1 plus is there and here 1 plus is there. So this is the actual compound here. Not this is plus 2 means don't think that oxidation state of iron here is plus 2. It is not plus 2. Here what it is here? Plus 1. Clear? Why? Because means this is the reason. Because of charge transfer. Charge means what is electron transfer here. Electron having charge, that is only. From where to where? Ligand to metal. And this is about the, you know, chemical reactions of HNO3. Clear? So next last concept here is uses of HNO3. So in this one, you know that it is mainly used in the manufacture of ammonium nitrate. Ammonium nitrate, not nitrite, which is used as a fertilizer. Clear? And second one, in the manufacture of explosives also, I already mentioned TNT, trinitrotoluene and trinitroglycerol, which are used as a explosive and which are prepared by the concentrate HNO3 only. Clear? Next one, pickling of stainless steel. Pickling means, you know, it is cleaning purpose of stainless steel, and you know, etching of metals. and also used as a oxidizer in the rocket fuel. In the rocket fuel, it is use some small amount of HNO3 will be used, which is act as a oxidizer. And you know, very important, it is as a reagent in the laboratory. In the laboratory also, you know, it is used as a reagent. And this is about the what it is uses of concentrated HNO3. Then we will go for the phosphorus, allotropic form of phosphorus. So next one is here concept allotropic forms of phosphorus. Clear ma? So as I already mentioned, allotropic forms of 15th group elements, that time I mentioned phosphorus exists in so many allotropic forms, but the main allotropic forms are allotropic forms of phosphorus are white phosphorus, red phosphorus and black phosphorus, and those we will discuss here one by one. Clear ma? So put the heading, first one is white phosphorus. Clear ma? White phosphorus. White phosphorus. Clear? So first here preparations are there. One preparation is there, and after then structure, and after then we will go for the properties. Properties I will write and explain because so many properties are there. Clear ma? So first one is here preparation. How we will prepare the white phosphorus. Clear? So white phosphorus is prepared from the phosphate rock. What is the formula of phosphate rock? Ca3PO4 twice. This is the phosphate rock. What it is here? Phosphate rock. ROCK. Clear ma? Phosphate rock is treated with the, you know, silica. Silica means SiO2. What we will call this is silica. Clear ma? Silica plus coke. Clear ma? So here coke. Clear? And this mixture is heated at around 1773 Kelvin. Then you will get the white phosphorus. What is the phosphorus formula here? P4. Clear ma? And along with that calcium silicate, and you will get the carbon monoxide. You will get the what it is, you know, silica is converted into calcium silicate, and calcium phosphate is converted into phosphorus, and carbon is converted into carbon monoxide. This is, you will get P4 is a white phosphorus. I will write simply white phosphorus. Clear ma? So balance the equation. How many phosphorus atoms are there? 4. But here how many are there? You know, 2 only. So multiply this one with the 2. When I multiply this one with the 2, how many calciums are there? 6. So that's why I have to multiply this one with the 6. When I multiply this one with the 6, how many silicons are there? 6. So that's why I have to multiply this one with the 6. Clear ma? So then you have to see the how many oxygen atoms are present here. Once you have to check it. Clear ma? Here you see PO4. PO4 means here how many oxygens are there? 4 into 2 8, 8 into 2 16, and here Si 6 into 2 12. Clear ma? So total how many are there? 28. But here you see 6 into 3 18, but we need that side how many? 28. 28 means how many difference? 10. So that's why I have to multiply this one with the 10. So that's why carbons will be 10. So this is a 10. Clear ma? So this is the preparation of white phosphorus. So white phosphorus, from which one we will prepare? We will prepare from the phosphate rock is treated with the silica in the presence of coke and maintaining the high temperature. Then you will get the white phosphorus. Clear ma? So next one is here structure. Structure of white phosphorus. Clear ma? So structure of white phosphorus. Clear? So how it will be means, and this is, you know, phosphorus, and these are lies. These phosphorus atoms are lies the corners of tetrahedron. This is clear ma? So this is the structure of the which one ma here? Phosphorus. Clear? So this is clear. So this is, you know, phosphorus forming how many bonds here? 3 bonds forming, 3 bonds and 1 free lone pair. So what is the, you know, hybridization? If you take here, hybridization is here sp3. Clear ma? Why? Because you know that in this case 3 bond pairs are there and 1, you know, what it is ma here? Lone pair. Clear ma? So this is sp3 hybridization phosphorus, and you know it will occupies, they lies at the corners of tetrahedron, and this is about the structure and preparation of which one ma here, white phosphorus, and then we will go for the properties. Clear ma? See now here, if you see the structure, and the bond angle is here, how much ma here, 60 degree. But actually sp3 phosphorus, what is the hybridization here, sp3 phosphorus is sp3 means, you know it should have the bond angle 108.9 degree, but how much it is there ma, 60. So it has so much angle strain, and angle strain is there. To avoid that angle strain, and these bonds will break, so that's why it is very very highly reactive. Clear ma? And how many pp bonds are there in this one, in the white phosphorus? You see 1 2 3 4 5 and 6. There are, you know, there are 6 pp bonds are present. pp bonds are present, pp bonds are present in white phosphorus. In what it is ma here, white phosphorus. Clear? But one phosphorus is making how many bonds here? 3 bonds. 1 1 2 3. So this is about the structure. Clear? And here I mentioned already preparation and structure of white phosphorus. Now here properties of white phosphorus. Clear ma? See, the first one is, it is a soft waxy solid. It is a solid. And next one, it is very highly poisonous. It is highly poisonous. White phosphorus is highly poisonous, and people which are working with the people who are working with the white phosphorus, and they develop here one disease called as a phosphorus. What is that disease name here? Phosphorus. What is this one? Is decay of jaw bones. That disease we will called as a phosphorus. So that's why it is highly poisonous. And also the boiling and melting point of white phosphorus are quite low. Why? Why? Because you know that the phosphorus structure you have already seen, it is a tetrahedra unit, and these tetrahedra, many of tetrahedra units are, you know, held together by weak van der Waals forces. So that's why they will have very low melting and boiling points. Clear ma? And you know, as I already mentioned, and phosphorus, you know, tetrahedral structure it is. And what is the bond angle in the white phosphorus? The bond angle between the PPO bond is 60 degrees. But actually how much angle should be present here? 109.8 degree it should be. Clear? But how many what is the angle here in the white phosphorus? 60 degrees. 60 degrees means it feels very stress. Clear? Angle strain, and due to that angle strain, and you know, this molecule, this phosphorus, white phosphorus is very highly reactive. Clear ma? So highly reactive form of, you know, it is highly reactive allotropic form of phosphorus, very highly compared to the red phosphorus and black phosphorus. You know, white phosphorus is very very reactive, and you know, so due to this high reactivity, it catches fire in the air with greenish glow, which can be observed, which can be seen in the dark, not in the light. Clear ma? So that we will called as a, that process we will called as a, you know, phosphorescence or chemiluminescence. Clear ma? So it catches fire in the air and with a greenish glow, which can be observed in the dark, and that process we will called as a phosphorescence or chemiluminescence. And it burns in air and produces dense white fumes. Clear ma? So when it is burned with the air and produces which one ma? P4O10. Balance here, phosphorus here 10 is there, so multiply this one with the 5. So that's why, and you know what you will get ma here? P4O10, and it gives the white fumes. Sometimes they will ask, and white phosphorus reacted with the oxygen and gives the white dense fumes, and white dense fumes are because of which one ma here? P4O10. Clear ma? So P4O10, and it is insoluble in water but soluble in CST, and it react with concentrate HNO3. It react with concentrate HNO3 in presence of inert atmosphere. So here very important reaction is there. So what is that one? White phosphorus. This is which one ma here? White phosphorus will react with concentrate NaOH solution. Clear ma? In where inert atmosphere. Why inert atmosphere? Because it is very highly reactive and it may react with the air, so that's why you have to maintain here inert atmosphere, and you have to maintain here temperature and inert atmosphere, use the CO2. Then what the compound you will get here is pH3 and sodium hypophosphate. Clear ma? So NaH2 and PO2. This is clear ma? So here what is the balancing you have to do? You have to do the balancing. Sodium hypophosphate, this is clear ma? What is the name of this compound? Sodium hypophosphate. Sodium hypophosphate. Clear ma? So now balance, as I already said how to balance this one. So it is a compound is a disproportionation reaction. So multiply this one with the 3 and 3 and you will get here 3 moles. Here how many phosphorus atoms are there? 4. So that's why I multiply this one with the 3. Clear ma? You are getting which one here? Phosphine. Very important. This same reaction again we will discuss in the preparation of the phosphine. And 3 NaOH and H2O, pH3 and sodium hypophosphate. Here minus 3, and if you calculate phosphorus here you will get 1. So this is the which reaction? 0. It is phosphorus oxidation state how much? 0. 0 to minus 3 reduction, 0 to plus 1 oxidation. This we will call as a disproportionation reaction. So white phosphorus. So next one is red phosphorus. Clear ma? So preparation, first one, how to prepare the red phosphorus. Previous we have discussed how to prepare the white phosphorus. So white phosphorus you take and heat the white phosphorus at 573 Kelvin in inert atmosphere. Maintain the carbon dioxide gas, almost carbon dioxide is inert gas. So that's why inert. Why? Because white phosphorus is highly reactive. If any air moisture is there, it catches fire and react with the oxygen. So that's why inert atmosphere must be maintained, and you will get the which phosphorus? Red phosphorus. Formulas are same. Here also P4. Here also what it is? P4. But it is red phosphorus and white phosphorus. Clear ma? So now what is the structure here you see? And it is the structure of this red phosphorus is like white phosphorus, but and these tetrahedra units are linked together by a covalent bond and gives the polymeric structure. Clear ma? So there only one P4 unit will be there, but here these P4 tetrahedral units are linked together by a covalent bond here. See clear? And if you write here, keep on writing, you will get the polymeric structure you will get. Clear ma? So this is about the structure and preparation. Now what it is here? Phosphorus properties. Clear ma? So if you take the properties, and white phosphorus is a soft waxy white solid it is, but here red phosphorus, so it is a violet red powder. It is a violet red powder. White phosphorus is a poisonous, but it is a non-poisonous in nature. You know that white phosphorus is having low boiling and melting points. Why? Because only one tetrahedral unit is there. The tetrahedral, among the tetrahedral units are the tetrahedral units here, P4 tetrahedral unit, another P4 tetrahedral unit are held together by a van der Waals forces, weak van der Waals forces. So that's why white phosphorus will have low melting and boiling points. But if you consider the red phosphorus, clear ma? It is what it is, red phosphorus, these tetrahedral units are and linked together by a strong covalent bond. So that's why it will have high melting and boiling point than the which one ma? White phosphorus. And it does not catch fire easily. White phosphorus is highly reactive. It catches fire with the air and gives the greenish glow. But it cannot catch fire easily. Why? Because it is a less reactive compared to the which one ma? White phosphorus. So that's why that I have mentioned here, it is more stable and less reactive than the white phosphorus. So it does not catch the fire easily, but it will react with the oxygen, but at high temperature, not at room temperature. White phosphorus will react with the oxygen at room temperature only, but red phosphorus, it is a red phosphorus will not react easily with the oxygen at room temperature, and temperature if you maintain, then you will get the P4O10, and it is a more stable form because it is a polymeric structure. So that's why it is a more stable form. So that's why less reactive. So less reactive, it does not catch the fire easily. Clear ma? And it is a polymeric in nature because it is a polymerase structure, and it does not react with concentrate NaOH. Very important. This is the difference. If you write between the differences between the white phosphorus and red phosphorus. White phosphorus will react with concentrate HNO3 and gives the phosphine and sodium hypophosphate. I have already discussed, but red phosphorus will not give phosphine and red sodium hypophosphate, because red phosphorus does not react with caustic alkali. Clear ma? That is about the preparations, structure and properties of red phosphorus. So next one is black phosphorus. Clear ma? So black phosphorus, it is two types. One is alpha black phosphorus, and another one is beta black phosphorus. Clear ma? So alpha black phosphorus will be prepared from the red phosphorus and beta black phosphorus is prepared from the white phosphorus. Clear ma? So how, first we will discuss about alpha black phosphorus. Take the alpha black phosphorus. To prepare this, take the red phosphorus and heat at 803 Kelvin temperature in a sealed tube. You will get the alpha black phosphorus. Clear ma? So it is easily alpha black phosphorus. Some properties are there. It sublimates in air easily. Clear ma? Sublimates means it is crystalline form. It will be easily converted into gaseous form. Clear ma? And it has opaque monoclinic or rhombohedral crystal. Clear ma? And it does not oxidize easily in the air. In the air, like red phosphorus, it won't easily oxidize in air. It is a bad conductor of electricity, which are on alpha black. Clear ma? Alpha black phosphorus is bad conductor of electricity. See the beta black phosphorus. White phosphorus maintain and high temperature means 473 Kelvin and very high pressure, then white phosphorus will be converted into black phosphorus. Clear ma? Now I am talking about whole phosphorus, means properties of totally, not alpha black and beta black. I am talking about properties of black phosphorus. Clear ma? It is highly polymerized form of phosphorus. If you see the structure here, this is polymerized. Clear ma? So many compounds, so many octahedral structure, like this is benzene ring like structure, so much polymerized. If you write like this, you will like a graphite structure. Graphite structure you already know. Clear? So it is looks like a graphite structure, so that's why it is a very highly polymerized form of phosphorus. Clear? So it is a very good conductor of electricity. Like it is structure of the black phosphorus is very similar to graphite. Clear ma? So it will have, phosphorus will have pair of electrons, lone pair of electron, so that's why they can carry the electricity. So that's why it is a good conductor of electricity and most stable among three. And black phosphorus is a most stable and inactive, very less reactive of phosphorus. It has a layer type polymeric structure, like which one ma? Graphite, and that I have given here. So this is the structure. You see, it is a benzene like, you see this is a benzene, right ma? So here carbons are there. Instead of carbons, what you have to write ma? Here phosphorus. So of 4 all are here phosphorus, and combined all this you will get the structure of, this is what it is ma? Here black phosphorus. Clear? So this is black phosphorus structure. So this is structure. It is a benzene ring. Benzene ring means like it is a benzene ring, all carbons will be there. Instead of carbons, what you have to put ma? Here phosphorus atoms you put, then you will get the what it is, and you combined, like again you combined here with the phosphorus atoms, highly polymeric structure you will get. And this is about the black phosphorus. Next one is differences between red phosphorus and white phosphorus, and sometimes they are asking in the PU examination. So what we have discussed, that is only I have written in the table form. Clear ma? First one is property, color. Which color? White phosphorus, white color. But I forgot to mention here, white phosphorus can also be called as yellow phosphorus. Why? When it exposed to light, it turns into yellow. When it exposed to light, it turns into yellow. So that's why white phosphorus can also be called as a yellow phosphorus. Clear ma? And here which color? Red, violet color I have already mentioned. State, it is a solid state and it is a powder state. And smell, it is a garlic. White phosphorus will have garlic smell and it is a smell, odorless. Action of air, and white phosphorus highly reactive and it react with air with greenish glow, that we will call as a chemiluminescence or phosphorescence, and no such a action. It will react with the air but at high temperature, clear, at not room temperature. Next, with the NaOH, I already mentioned red phosphorus reacted with the concentrated HNO3 and gives the phosphine and sodium hypophosphate, but red phosphorus will not react. And the next one, it is a poisonous and it is a non-poisonous, and solubility insoluble in water but soluble in CST, but red phosphorus is insoluble both water and CST. So this is about the and allotropic forms of the which one, my here, phosphorus.